In this video, we will see what's perhaps the simplest example of a differentially private mechanism. Suppose you want to know what fraction of a population does something illegal, like, say, taking drugs. This is a problem that the American army actually had to solve at some point. Of course, the problem is that if you ask any person directly, he or she will likely not answer truthfully. And this is because such a direct survey breaks privacy. The key to not fully break privacy while retrieving some information to introduce randomness, as we discussed it in a previous video. So one trick that can be used is to ask each respondent to secretly throw a die. If the die yields a 1 or a 2, the respondent will simply answer no to the question, did you do something illegal? If the die yields a 3 or 4, he will answer yes. And finally, if the die yields a 5 or 6, he will answer truthfully. Importantly, only the respondent knows on which number the die fell. So the surveyor cannot know whether the respondent was answering truthfully or whether he answered what he answered because the die told him to. Now, suppose we surveyed 300 people this way, and let's say we had 130 yes and 170 no's. We know that 1 out of 3 of these surveyed people had to answer yes because of the die, while another 1 out of 3 had to answer no. So then, once we've subtracted 100 yes and 100 no's, we obtain 30 yes and 17 no's. These were the truthful answers, and so we know that around 30% of the surveyed people actually did something illegal. We actually retrieved useful and reliable information, but crucially, we did so without breaking privacy. For any individual respondent, we cannot tell whether he actually did something illegal. It's even better than that. Using differential privacy, we can actually quantify how much privacy was lost by any respondent in the worst possible case. More precisely, differential privacy tells us to focus on the ratio probability that the answer is yes, given that the respondent did something illegal, divided by the probability that he answers yes, even though he did nothing illegal. We actually know precisely what this ratio is. It is equal to 2/3 divided by 1/3, which is equal to 2. Which means that in the worst case, when a person were being truthful, then the surveyor can at most only double its doubts on the respondent having done something illegal. A more precise interpretation of what I've just said informally here can be derived from the Bayesian interpretation of differential privacy. In particular, we have here the probability that the response is illegal equal to yes is at most e to the log 2, or this is equal to 2, times the probability that the response of someone who did nothing illegal being yes. And through a similar computation, we also have the probability that the response of someone who did something illegal being no is at most e to the log 2 of the probability that the response is no for someone who did nothing illegal. Now, there is a slight technicality here using differential privacy because here the database is actually always only a singleton. It cannot be an empty set and it cannot be more. But if we say that legal versus illegal is at distance 1, we conclude that our randomized survey was log 2 differentially private. So log 2 is about 0.69. In other words, it is differentially private for epsilon equals to log 2 and delta equals to 0, which, as we've discussed, is a pretty good privacy guarantee.